The second example I'm going to go on to is an illustration for our third type of t-test, our independent samples t-test. And this is the same example that we've talked about for one of our previous, I think it was also an independent samples t-test previously. This is an organizational psychology study where they were looking at the things that might impact people's judgment or kind of rating of somebody who's applying for a job. And specifically, they're looking at the differences between hearing essentially someone's skills or their kind of attributes auditorily, so hearing them read it out, versus reading that same information in a written way to test the hypothesis that there's extra kind of information that you get or extra pieces of kind of benefit that you get from hearing the skills versus just reading the skills. So what we're looking for here, the stuff written in red is just the addition to what we looked at previously, is to see whether the person's speech would communicate information about their intellect better than their written words and therefore be more likely to get hired. So our dependent variable here is the actual likelihood of being hired. It's a higher rating on a scale. And our independent variable is the two different groups, the two different conditions, transcript versus audio. And because this is an independent samples t-test example, that means that these two groups are between subjects' manipulations. They're two independent groups, two separate groups, unlike the previous example where it was the same people doing two of the conditions. Okay, so for our independent samples t-test, we know that our assumption of normality applies to the distribution of the DV within the two different groups, within the two separate groups. So what we need to check is to see if our outcome variable, which here is the higher rating, is approximately normal for the audio group, but also separately for the transcript group, for the written group. And that's what our histogram on the right-hand side is showing. It's showing the distributions within the two different groups. And then our numeric summary statistics on the left-hand side, which is showing the average scores between the two groups and then the variability around those scores. So you can see that there's a similar spread of scores in terms of the minimum and the maximum between the two groups, but you can also see that the average score is a fair bit higher in the audio group compared to the transcript group. The mean score in the transcript group was 2.8 between 0 and 7, and the mean score was 4.7 in the audio group between 0 and 8. So just by looking at these numbers, we can see it looks like there might be a difference. It looks like there could be higher scores on the higher rating, HIGHER scores on the higher rating in the audio condition group compared to the transcript group. But what we need to do to test the data formally within the t-test analysis is to see if that's a substantial enough difference to likely reflect a real difference in our population. So in order to have a look at the normality, we had a look at the histogram on this previous slide 32, and we can also conduct the Shapiro-Wilk test, which is the same test we did for the last couple of examples. And what we can see here is that we've got the Shapiro-Wilk results within the two different groups. And again, that's because this assumption of normality of our dependent variable is that the variable is normally distributed within the two separate groups. So we need to test it separately for the two separate groups. And what we can see here is that, again, both of these Shapiro-Wilk tests are non-significant. So both of the Shapiro-Wilk tests have p-values bigger than 0.05, which in conjunction with looking at the histograms on the previous slide and seeing that they looked approximately normal, we can see that that means that they are approximately normal, that this assumption is met here. So that's good. That was our first assumption. Our second assumption is that the variation in scores or the spread of scores is approximately even between the two different groups. And we can test that using what's called Levene's test for equality of variances. This is the syntax in Stata to do that, and this is the output it gives us. So what we're testing here is that the variation, which is represented by the standard deviation of scores, is about the same, is approximately the same between the two groups. So you can see just by looking at the numbers that there is a slightly lower standard deviation in the transcript condition, a standard deviation of 2.0, and a slightly higher standard deviation in the audio condition, 2.26, but it's a very, very small difference. And the results of the actual statistical test itself, the significance test, which is this first row here, just ignore the next two rows, just the first row here. This is our Levene's test statistic, and our p-value for that test statistic is 0.8, which is bigger than 0.05, which we can interpret as being non-significant, which means that the assumption is met. So if we had a significant result here for Levine's test, if Levine's test p-value was less than 0.05, that would mean that there's a significant difference in the variances between the two groups, which would mean that our assumption is violated. So we don't actually want a significant result for Levine's test, just like we didn't want a significant result for the Shapiro-Wilk test. So what we've got here is a non-significant result, which is good, which means our assumption is met. So recapping our assumptions for our independent samples t-test, we know that our dependent variable is on a numeric scale because we had a look at the data, and also we know the design of the study. We know that the higher ratings are on a 0 to 10 scale, and we know that each person has a score on that scale, so that means it's a numeric scale. We've looked at the distribution of our DV within our two different groups, and we can conclude that yes, it is normally distributed. We've also looked at the variances in our DV between the two groups, and we can see that they are about equal. There's about an even amount of variation or spread of scores between the two groups. And we also know as a condition of our sampling design that our observations are independent. So the two groups are completely independent, and then the people within each of the groups are also independent. So all of our 4 assumptions are met there for this particular test. So if we wanted to run our independent samples t-test, then this is our status syntax at the top here, t-test, high rating by condition, and this is our output, which again looks reasonably similar to the other 2 t-tests that we've done previously. We can see the descriptive statistics for both of our 2 groups. We can see our t-test results here with degrees of freedom, and we can see our p-value in the middle here. So this 0.0127, that's our p-value that applies to this particular t-test. So because that p-value is less than 0.05, that means we have a significant result, which means we have a significant difference between the 2 groups. And looking at the 2 means, we can see that the mean is significantly higher in the audio condition group compared to the transcript group. So that means that people were more likely to be hired if their skills were read out auditorially compared to their skills being read in a written way as a transcript. So we can write something like there was a significantly higher rating in the audio condition compared to the transcript condition, and then quote our t statistic and our p-value. We can also again measure the effect, the size of this difference, and in this instance I'm going to use an unstandardized effect size measure, kind of similar to the percentage difference that I used in the previous couple of examples, by just looking at how big the difference is between the 2 groups. So group 1's mean is 2.8, group 2's mean is 4.7. That's almost a 2-point difference. It's a 1.8 point difference, almost 2-point difference. So I could say, to communicate the size of that difference to whoever's listening to me talk about these things, we can say something like there was on average an almost 2-point increase on a 0 to 10 scale in higher ratings. And so giving the reader an idea of what the scale is helps us to interpret how big or how substantial that 2-point increase is. Because if this was on a scale from 0 to 100, a 2-point difference is a very small difference, whereas on a 0 to 10 scale, a 2-point difference is actually quite a big difference. So that's where that's come from. We can also talk about our confidence interval. So the 95% confidence interval around that difference ranges from 0.41 to 3.24. And we're interpreting that as saying that we're 95% certain that in the population, the benefit that you get from being in the audio condition ranges from 0.41 units to 3.24 units. So that was a measure of an unstandardized effect size, but we also know that standardized effect sizes can be useful as well because they can give us something that we can directly compare from study to study. So a 2-point increase is useful to know if we're on a 0 to 10 point scale, but if I want to compare the size of this effect to a different study that used, say, an 100-point scale, then I can't directly compare that 2-point increase. And that's the benefit of having something like a Cohen's d, which is our standardized effect size measure, because they're directly comparable from study to study and from variable to variable. So let's do that. So Cohen's d in this instance is just one group's mean minus the other group's mean divided by the pooled standard deviation, and we need to calculate that separately. Unfortunately, Stato doesn't give that information to us, but you'll find the formula for that on your week 7 slide deck. So one group mean minus the different group mean divided by the pooled standard deviation gives us a Cohen's d of 0.84, and that means that there's about a 0.8 standard deviation difference between these two groups. And we can interpret that as a large effect, as quite a big difference, quite a big improvement in higher ratings that you get from somebody listening to your skills through hearing you speak, say, compared to, say, reading your CV, reading your resume. So it's quite a large effect. The last thing that we'll talk about in this week's kind of recap lecture is just talking about what I mentioned at the start of today, which is looking at what kind of test you should pick in which circumstance. So as we've gone through each of the 3 different t-tests, I've talked to you about what kinds of research questions, what kinds of hypotheses are appropriate for each of them. I've also talked to you about the kind of design that's appropriate for each of them, and also about the variables that are involved in each of them. Because I think that flowchart's just a very useful thing, I've put together a little bit of a flowchart here, but keep in mind that this is going to expand when we start doing more different kinds of tests. So we've only done 3 different tests so far, 3 different t-tests, so this is a relatively simplistic kind of diagram, but we'll build on this through the rest of the semester. So we're going to start up the top with how many variables are there in your hypothesis. So if you think about the research hypothesis, how many variables are involved in that hypothesis? If it's one variable, then the kind of research question or the kind of hypothesis is going to be comparing the mean of some numeric variable to some external score, some other mean or some other value. That's the kind of thing you're going to be doing, in which case you'd be doing a 1 sample t-test. If, on the other hand, you've got more than one variable in your hypothesis, if you've got 2 variables in your hypothesis, then the kind of thing you want to do is to compare the mean of a numeric variable between groups. So to compare the mean for one group with the mean of a different group to see if they're significantly different. And there's 2 ways you could go about doing that. You could have 2 independent groups, 2 separate groups, in which case you'd be looking at an independent samples t-test. Or you could be having 2 related groups, in which case you could have a paired t-test. So as I said, this diagram is relatively simple at the moment. It will get a bit bigger as we add more tests into our arsenal, but hopefully it'll help kind of put things in perspective in terms of the things that we've done thus far. So some brief conclusion, end of our revision time. So hopefully this week's given you a bit of an opportunity to take stock of where we are thus far, to reiterate some of the important concepts, to kind of catch your breath a bit if you're feeling a little bit overwhelmed with it, so that you can feel ready to get into the new content next week. I really want to reiterate that if you're feeling a little bit unsure about any of these concepts, then go back to the relevant lectures where we first talked about them. As I said at the start of today, particularly because you've learnt more now, if you go back and revisit some of the earlier lectures where we talked about those important concepts, the fundamental concepts, it'll probably make more sense to you now because you've got a bit of a better sense of perspective. What we're going to go on to next week is a different kind of test, which is called a correlation, looking at correlation coefficients. These tests are for different sorts of research questions. And what you'll be pleased to know is that there are so many correlation memes on the internet, many, many more than we have for t-test memes. So you're going to be even more inundated with memes compared to what you've had so far. These are just a couple of them, but there's so many more. So get excited for correlations coming next week.